Hey everyone, let's continue our discussion on linear regression and learn how to calculate the simple linear regression equation, how to determine if the regression slope coefficient is significant, and determine how well the model fits the sample data. So if you're ready, let's get started. Simple linear regression is a statistical method that used to describe the linear relationship between two variables. In the prior video, we learned how to develop a scatter plot to visualize any potential relationship between two variables. We will now expand upon this to see if there's a linear relationship. Simple linear regression analysis is when we have a single independent variable denoted by x to explain the variation in a dependent variable y. So in the example here, on the x-axis, we can see this is years worked at Midwest Company, and on the y-axis is the dependent variable. This is the number of sales achieved. With simple linear regression analysis, we are trying to find the best fitting line that represents the relationship between these two variables. Let's now review the equation for the population linear regression model. The population model for the simple linear regression represents the relationship between x and y. Y is a dependent variable. X is the independent variable that we're hoping to see if there is a relationship that we may explain what's going on with the y. So beta sub 0 is the population's y-intercept. This is the constant in the model. Beta sub 1 is the slope of the population regression line. The slope tells us the direction of the relationship, if any exists, whether it is positive or negative. Together, these two are the regression coefficients that will be used to explain the model. Epsilon is the random error term, which we're trying to minimize. We won't be focusing on that too much in this chapter. So let's look at the meaning of the regression coefficients more closely. The regression slope coefficient, or beta sub 1, measures the average change in the value of the dependent variable y for each unit change in x. So if we see a positive slope for each unit of x, then y will increase for each unit change in x. If the slope is negative, we will see a decrease for each unit change in x. The intercept, or beta sub 0, this is the value of y when x is 0. So if we imagine the regression line in the scatter plot, this is where the line crosses the y-axis. The least squares criterion is how we'll be finding the best fitting line. Here, we are trying to find a line that minimizes the sum of squared prediction errors, or residuals. The residual is the difference between the actual value of the dependent variable and the predicted value from the regression model. Here is the equation for the best fitted line for this data. So the red dots here represent the actual values, or the values from the employees in terms of how many years they have worked at the company and their sales. The residual is the difference between the dots and the value from the best fitted line. So for example, this employee here had 312,000 sales and was with the company for 4 years. The predicted sales is 390,000 for 4 years. Therefore, the residual for this data point is 312 minus 390, or negative 78. Since we can't study the entire population, we must use an estimated regression model based on sample data. So the formula gets simplified down to the pieces that we'll use in order to estimate the regression model. This y with a little hat over it, this is the predicted y value. Beta sub 0 is now lowercase b sub 0, and this represents the intercept still. Beta sub 1 is now lowercase b sub 1, and this still represents the slope. Then x is the value of the independent variable. Now, we do have these equations here to help us find the intercept and the slope, but we'll be using Excel to help us with these complex calculations. The goal when finding the best fitted line is to find the line with the smallest sum of squared residuals possible from the sample data. All right, now let's work on a practice problem. Here is problem 14-25, which is a continuation of 14-12 in the prior video. A regional retailer would like to determine if the variation in the average monthly store sales can in part be explained by the size of the store measured in square feet. Let's focus on part A first. We are asked to compute the simple linear regression model using the sample data to determine whether variation in the average monthly sales can be explained by store size. We need to interpret the slope and the intercept coefficients. In this video, we'll use the output from Excel using the data analysis toolpak. Here are step-by-step instructions for the regression option in Excel. A couple of key points. You'll want to select the dependent variable for the Y input range and the independent variable for the X input range. Always remember to check the labels box if you include the header row for your sample data, otherwise you'll get an error. Finally, if the problem specifies confidence level that is different from 95%, you can change that as well. This will be important later when we are talking about the confidence interval for the slope coefficient. Then you click on OK. Here is a screenshot of the data from question 25 on the Excel sheet and the regression tool. I have selected range B1 to B22 for the Y range since the average monthly sales is the dependent variable. I have also selected the range A1 to A22 for the X range since the store size is the independent variable. I also checked the labels box since row 1 was included in the range. After clicking on OK, here's a snippet of the output. I'm focusing on the bottom table in the regression output in Excel. First, it's important to identify our variables for the regression coefficients. The intercept is B sub 0, and the store size or square feet is B sub 1. Notice how it lists the name of the independent variable. This is because I checked the labels box, so this can be helpful when identifying if you've done it correctly. We will use the regression coefficients to create the regression equation. The Y variable, or the dependent variable, which is sales, is equal to the intercept plus the slope times the store's square feet. We are hoping to see how much the square feet of the store can explain the average monthly sales. So plugging in the coefficients for B sub 0 and B sub 1, we get the average monthly sales for the regression equation is 171,205.83 plus 25.32 for the slope. Note, since the slope coefficient is positive, we have the plus sign. If we had a negative slope, we would need to change this to a minus sign. So let's interpret each coefficient. First, the intercept. This is the estimate for the average monthly sales when the independent variable X, or the store size, is 0. Now we know it is not possible to have a store size of 0 square feet, so the Y-intercept does not have a meaningful interpretation in this problem. What's more important is the slope. So this is 25.32 regarding the square footage or the store size. The slope shows us how the average monthly sales will change as the store size is changed by 1 square foot. We know this is a positive increase, so for each square foot increase, the average monthly sales are also predicted to increase. Specifically, it will increase by $25.32. Finally, here is the regression equation, formally replacing the dependent variable or sales with Y and the independent variable or square feet with X. Let's now learn how to run a hypothesis test for the significance of the regression slope. If you recall from the prior video related to the correlation coefficient, since we've used sample data to calculate the sample correlation coefficient, we needed to conduct a test of significance on that coefficient. We will do that again here to test if the regression slope coefficient, or beta sub 1, is statistically significant. Here we have the hypothesis test, which is a two-tailed test. A slope of 0 means there is no linear relationship and would not be useful in explaining the variation in Y. If the slope is not equal to 0, meaning some positive or negative number, then there is some linear relationship. Excel will provide us with the test statistic t as well as the p-value we need to conduct our testing approaches. But it is important to understand how to determine the test statistic as well as how to read these values in the Excel output. Here is the formula for the t-test statistic, where we'll take the estimated slope from the sample minus the hypothesized slope. In this case, we're setting it to 0 since we hypothesized that there is no relationship. We're looking for evidence to tell us whether there is a relationship. Then underneath this is the standard error, specifically the standard error of the slope. The degrees of freedom will be n minus 2. For the critical value or the cutoff point, we can use Appendix F or we can use Excel. If we are using the p-value approach, recall that the p-value rule states that if the p-value is less than alpha, we reject the null. Note, here it says that alpha divided by 2 because it's a two-tailed test for both sides of the curve. Let's review the estimate of the standard error for the least square slope, which is this formula here. Just as the distribution of possible sample means has a standard error, the possible regression slopes also have a standard error. Here on the left, these three samples have a larger standard error due to the variation in the slope values for each line. Now, compared to this example, this would have a smaller standard error since all of the lines have a similar slope value. We will fortunately be using Excel, but again, conceptually, we need to understand that there is a standard error of the slope that needs to be accounted for when we run the hypothesis test. Let's continue working on problem 14-25. This is the same regional retailer who wants to see if the variation in average monthly store sales can in part be explained by the size of the store measured in square feet. Now in B, we want to test for the significance of the slope coefficient of the regression model using a level of significance of 0.05. In other words, we're going to test for the significance of beta sub 1 in the regression model. The null hypothesis states that the slope is equal to 0. This means there is no linear relationship and is not significant. For the alternative hypothesis, it states that the slope is not equal to 0. If that is the case, then that means there is a linear relationship and it is significant. The alpha that was given in the problem was 0.05. First, we need to find the degrees of freedom, which is n minus 2. So recall, we were looking at 21 stores. So we take 21 minus 2 and we get 19. Let's use Excel to calculate the critical t value. Since it's a two-tailed test, we will input t.inv.2t and then 0.05 for the probability and 19 for the degrees of freedom, and we get 2.093. This is a negative 2.093 and a positive 2.093 for the two sides of our curve. We have already run the regression analysis previously, so here is a snippet of those results again. You can see here, Excel has already given us the t-test statistic of 7.078, but let's go ahead and calculate here to validate it. The slope coefficient, or b sub 1, is here, which is 25.316, and we subtract 0 since we hypothesized that it is 0. The standard error of the slope coefficient is also given to us here at 3.5767. So we divide by that and we get 7.08. So that checks out with the regression output. So the conclusion is 7.08 is greater than the critical value of 2.093. We reject the null hypothesis and conclude that the population slope coefficient is significant and there is a linear relationship. Let's talk about our last topic in this video and the concept of the coefficient of determination. First, let's talk about the concept of the sum of squares, which is the measures of variation in the regression analysis. The formula here is SST equals SSR plus SSE. Let's look at what each component means carefully. The total sum of squares, which is this formula right here, this is the measure of the total variation in the regression analysis. Now, the SSR, or the sum of the squares regression, this is the measure of explained variation. This tells us how well the regression model represents the data that we've collected. Then SSE, this is the measure of unexplained variation. So these are the errors between the predicted values from the model and the actual data. Unexplained just means that there could be some variation in the data that is not explained by the independent variable, but by some other factor. While we have these formulas, again, we're going to use Excel to help us out, so we don't have to calculate it by hand. However, we do need to understand the relationship between SST, SSR, and SSE. Looking at the regression analysis we ran before, we're going to identify where in the output we can find SST, SSR, and SSE. It is here in the ANOVA table, and it's the second table in the output. SS is the sum of squares. So in this column, we have the sum of squares regression, or SSR, the sum of square residuals, which is just another way to say errors, so this is SSE. Finally, we have the total sum of squares, or SST. And as you can see, we can add up the SSR and SSE to arrive at the total. So the sum of squares concept we have been discussing builds up to the concept of the coefficient of determination, or R squared. This is the portion of the total variation in the dependent or Y variable that is explained by its relationship with the independent variable. R squared will be somewhere between 0 and 1. Here's the formula for R squared. We will take the sum of squares regression number and divide it by the total sum of squares. Note that for the coefficient of determination for a single independent variable case, R squared is the same as the square of the sample correlation coefficient, or lowercase r, that we learned about in the prior video. Let's wrap up question 14-25 now and answer C to identify what percentage of the total variation in average monthly sales can be explained by store size. Here is the same regression output again. So to get R squared, we look at the sum of squares section in the table here. We take the SSR, that is a top number for regression, and divide by SST, which is the total sum of squares, and we get 0.7250. The better the fit, the closer the R squared will be to 1. R squared will be close to 0 when there is a weak or no linear relationship. As you can see, the regression output also provides us with the R squared in this table here, which is at the top of the full regression output. The multiple R is the correlation coefficient that measures the strength of the linear relationship between the two variables. So if we take 0.8515 and square it, we get 0.7250. So that checks out from the prior slide. So we can say that approximately 72.5% of the variation in average monthly sales can be explained by store size. In this video, I won't be covering in detail the F ratio and p-value shown here for testing the significance of the population coefficient of determination, notated by the lower p squared or rho squared. However, I do want to point out the key numbers in the regression output to do this. Here is the MSR, which is the SSR divided by the degrees of freedom of 1. MSE here, and that is the SSE divided by the degrees of freedom of 19. Then the test statistic F is just the ratio, or MSR divided by MSE. We would then use the test statistic F to compare to the F critical value that you can find in the appendix H for the critical value approach. Finally, the significance F is the p-value if we were to use the p-value approach. The null hypothesis is that the population coefficient of determination is equal to 0, and the alternative hypothesis is it's greater than 0. Okay, that wraps up this video on simple linear regression. In the last video for chapter 14, we'll learn about the different uses of regression analysis.